Various components are located together, maybe for latency reasons, maybe for resiliency reasons. So we have a number of approaches for scheduling pods, and we'll cover these in a little bit more detail one at a time. So we've got node selector, we've got this pod affinity, anti-affinity, got these taints and tolerations. We have the ability to do pod affinity, and I'll explain what all of these are in a little bit. And then finally, the kind of nuclear option of a custom scheduler. So let's talk about the node selector first. This is the most straightforward, the most basic version. Essentially, all we're doing is we assign a label to our node. So incidentally, on my screenshots, everywhere you see the K, that's the alias for kubectl. I'm just lazy, so I don't type it out. So what we do is we label a node with a key value pair. So in this case, I'm labeling this AKS node with team equals foo. And then in the pod spec for my deployment, in my YAML, what I'm doing is I just specify a node selector, and I give that key value pair. And this works well. This is quite straightforward, but it's a little bit limited. All you can do is select a node. If that node doesn't exist in your cluster, then your pod won't be scheduled. So this is where, if you want a bit more control, we can move over to node affinity and anti-affinity. So this allows us to attract pods to nodes based on their labels. So initially, the concept is similar, except now what we're doing is we're not matching purely on just an equality. We've got a number of other conditions we can match on. So now what we can do is we can choose to whether match on in or not in. Obviously, that's the anti-affinity side. Same with exists and does not exists. The nice thing is the key difference with the node affinity is we can be selective in how demanding we are. So previously with the node selector, if that node without the label didn't exist, your pod wouldn't get scheduled. Now we can be a little bit more flexible. So how do we do this? We use a couple of catchy terms. One's called required during scheduling, ignored during execution. Try saying that a few times. That's a bit of a mouthful. Essentially, what this is doing is this is very similar to the node selector. This is saying this is a hard requirement. I want this label to exist. If not, my pod won't get scheduled. Now, alternatively, what we can do is we can say this is preferred. So preferred means, ideally, if there's a node there with that label, we'll use it. If not, we'll put it somewhere else. If you're looking at this, and it's quite long, you're wondering what this ignored during execution bit means. Well, the spec for this actually has a third option, which isn't implemented yet, which says required during scheduling, required during execution. So the key thing with these labels and these demands is they're around the time when the pod's being scheduled. So if you add a label to a node once a pod is already on there, it won't get evicted, it won't get kicked off. That's what this third option was potentially going to allow you to do. And as it turned out, it's not been implemented yet, and now there's other ways you can do this as well, which I'll talk about in a second. So if we have a look at the YAML, the pod spec for this, it's a little bit more wordy. So now obviously we've got this node, the affinity section. We've got that term, which we're saying is required, and now we're matching. So this is very similar to the node selector. I'm achieving the same thing. Obviously, it's a little bit more verbose, but it gives me more power. So I can specify multiple values, for example, there. If we look at the preferred one, so this is now saying ideally, it looks very similar. We've got a couple of extra terms. So obviously, we've got this preferred. Then we've got this weight. And the weight is there because there can be multiple nodes which meet the requirement, and the weight is used to try and figure out which one to pick, basically. So in this example, I'm using a label which is one of the defaults, I think, on AKS. It's just the instance type. So for example, I'm saying I want this pod to be on a DS1 V2 VM, for example. So these node affinities, they're quite good, but what if we want to have the ability to remove pods from a node if they don't match the requirements? This is where we have the taints and tolerations concept. So in this approach allows you to repel pods from a node based on taints. So what we do is we taint a node, and then the pods tolerate that taint. If you don't have a toleration, you won't be scheduled on that node. When you define a taint and toleration, there's three elements to it. So we have a key and a value, similar to the labels. And then we have the third option, which is the effect. So we have a choice of no schedule, which the name suggests, don't schedule the pod. Prefer no schedule, again, obviously a softer requirement. And then no execute. So this time the no execute will actually evict pods which don't tolerate the taint on a node. And actually, Kubernetes does this itself. It will taint nodes based on certain issues that are arising in the cluster. So if your nodes are running out of disk space or memory, Kubernetes will actually apply a taint to that node, and that's how pods potentially get evicted from your cluster. Sorry, yeah, that last point. If we have a look at how we do this, so this time now we're going to use the kubectl taint node command, and we supply the key value, key name, value name, and then the schedule. Once our node is tainted, for example, if I've got this deployment on 3-node cluster without toleration, what we're seeing is actually, ordinarily, by default, we would see the distribution of the pods across the nodes, and we're not. We're seeing 2 on one node, 1 on the other, and nothing's using that node 0. So what we now need to do is apply a toleration in our spec. So now in our pod spec, what we can do is we specify toleration. We give it the same key value pair, and then we say no schedule. When we apply that, then our pod can basically tolerate that taint, and it will be scheduled on that node. If you're wondering what this toleration seconds is, I think this is a little bit confusing personally. So if you don't specify toleration seconds, and you have a toleration on your pod, when a node is tainted, the pod will carry on running. If you specify toleration seconds, you're basically giving, that's how long the pod will carry on running before it gets gracefully evicted from the pod. So to me, it sounds a bit confusing because I'm tolerating the taint, but I'm specifying seconds, and then it's getting kicked off. But that's how that works. So if we now look at the same deployment, this time with the toleration for that taint, we're now seeing equal distribution across the 3 nodes. So far, we've talked about basically picking a node for our deployment, moving pods. Often when we have our applications, we need more control over where we deploy our application based on what else is running on that node. So not just the node itself, but what's running on it. And this is where inter-pod affinity or anti-affinity comes in. Often we just call that pod affinity. So this allows you to select nodes based on what pods are running on it. So why would we want this? So this is where we want to make sure that components of our architecture are running together. So let's say we want the cache to run alongside the application. Or conversely, we want to split things up. So we want to ensure, for example, that maybe multiple instances of our application are running across fault zones. So that if one of the fault zones, one of the VMs goes down in a fault zone, we don't lose the whole application. We don't lose both instances. Of course, Kubernetes will restore it, but it takes a few seconds. So we have similar constructs around strictness. So again, very similar, required during scheduling, ignored during execution. We have this new construct, topology key. So all the other labels, they're to do with the pods. The topology key, this is a little bit confusing, so hopefully the next few slides will clarify a bit. Talk about what level of the architecture, of the infrastructure, this anti-affinity is applied. So typically you might apply it to host name. So you're saying, I don't want these pods on the same machine. But you can just as well specify availability zones or racks or fault domains. You don't have to be, it doesn't have to be down to a single machine. What you're doing is you're separating out across different zones. That label, as I'll show you in a second, is actually on the node itself. So let's have a look at one of these. Again, hopefully becoming quite familiar now. So same bits there, and then this topology key. So just to reiterate, these labels are being matched on the pods. This topology key is matching on the node. So this is a node label, whereas these are looking for looking for keys, labels within your pods. So let's try and visualize this a little bit. So I've got this application, I've got 3-node cluster, and I've got 3 replicas of each of this web and cache. And what I want to do is I want it to be evenly distributed. I want web and a cache in each one of these nodes. I don't want it to be anywhere else. Now we could take a chance. Often Kubernetes does try and balance things out. Obviously in this example, there's nothing else running on the cluster. There may be other applications running. So we want to make sure that we are taking control of that. So how would we do this using Taints? Pod affinity. What we do is for our web component, what we do is we say we want pod affinity for the cache component. And we mark that as a preferred one because the cache may not be running yet. Those pods may not be running yet. but we want anti-affinity against the web components. So that's going to repel the pods to make sure they go on different nodes, and then the affinity will make sure they get attracted. And we're using the host name in this case, because we've got three hosts. So when I deploy that, Kubernetes will basically deploy 3 instances across the 3 nodes. Now it's time to deploy the cache. And again, similar concept. This time with the cache, what we're going to do is we're going to do affinity. We're going to attract to the web pods, but we're going to anti-affinity the cache pods. And by doing that, what we're doing is we're repelling the cache from each other to put them on individual nodes, but we're attracting the web. When we do that, we get that that we expect. So hopefully that gives you a better idea of how to control that. Let's have a quick look at YAML file. Hopefully people can see that at the back. So this is that example there. Just to show you quickly, so we've got the pod anti-affinity, and then we've got the pod affinity. You can specify multiple things here. That's what we're doing. So here we're matching for the component web, and then we're doing anti-affinity for the cache. Sorry, the other way around. And then for the cache, rather, let's get the right way around. For the cache, we are doing anti-affinity for the other cache pods, and we are doing affinity to the web component. Then when we deploy that, what we see is we get the behavior we expected. So now we've got 3-node cluster, and we've got each component is distributed evenly and paired up across those nodes. So as you can see, there's quite a lot of capability within the kind of built-in options in Kubernetes for controlling the pod kind of distribution, the pod scheduling. If none of these options suffice, you have a kind of nuclear option, which is to write a custom scheduler. You can write the schedule in any language you want. It just needs to be able to access the API server. I say just, that's quite tricky. That's quite hard. But broadly speaking, you just need to access the API server. And then what you do is in your pod spec, you can actually specify the scheduler name. So you'll specify the scheduler name. That will be the name of the deployment. And Kubernetes will basically, so there's an example in the documentation, or certainly on a blog post, where somebody's written it using bash. So randomly assign the pods to any of the nodes. Hopefully you don't need to do that. OK, so that's around pod placements. Let's move on to taking a little bit more control. So what if I want to have control of the resources I'm deploying? Maybe I want to apply some custom policies, saying that when you deploy things, you must have certain labels. You must not use certain resources. And maybe I want to inject some additional logic when I do a deployment. This is where you can start using things like admission controllers. So admission controllers is basically code that intercepts the API requests and allows you to run some logic before that request is actually persisted in etcd. There's kind of 3 variants, or there's 2 really. It can be a mutating admission controller, which modifies objects and can create new objects. It can be a validating one, which is its job is just to inspect and basically reject something. They can't mutate the state, and there can be both, mutating and validating. These things are basically built into the Kube API server, so they can be enabled or disabled in the Kube API server. Now, if you're running in the public cloud and you're running a managed Kubernetes service, which is what I think a lot of people are doing now, you have limited options in this. You don't have control of the Kube API server. You can't actually choose what you run. So you'd argue these are a little bit limited. And they're also compiled into the API server binary. So if you wanted to create your own, that's not so straightforward. We'll look at how we can work around that in a second. So there's a number of built-in ones. I'm not going to talk about these in great detail. I'm not going to talk about them at all, other than 2 of them. Let's have a quick look where they sit in the lifecycle of the API. So I do an API request. It hits the HTTP handler, goes through some authentication and authorization. Then we run the mutating admission controllers. So these things are mutating the state, potentially mutating the state of the resource I'm just sending through the request, or maybe even creating a new resource. Then we have some object schema validation. So you can hopefully understand that we do the schema validation after we've done the mutation. Then we run the validation controllers. Again, we want to run the validation controllers after the mutations happened, not before, because obviously we can bypass validation otherwise. then this request is persisted into etcd. And once that request is persisted in etcd, then another controller will pick up that request. So if it's a deployment, the deployment controller picks that up, goes and does what it needs to do. Within the mutating and validating admission controllers, there's two special controllers. And they're the mutating admission webhook controllers. And they're the ones that allow us to add some logic without needing to write a whole admission controller. So what's cool is we've got these two webhooks, mutating admission webhook and validating admission webhook. And as the name suggests, the mutating one allows us to mutate resources or create brand new ones, or the validating one allows us to block the resource creation. Because they're webhooks, they can invoke a HTTP callback, so industry standard stuff really. And the nice thing is the logic for this doesn't need to be compiled into the API server. And the logic doesn't even need to be in the cluster. It can be hosted outside of the cluster as well. Now, if you're doing mutations, again, you need to be able to authenticate against the server, the API server, so that can be a bit tricky if you're outside the cluster. But certainly validation doesn't need to be. So let's take a quick look at these webhooks and see how they work. So I have got a webhook here. So hopefully everyone can see that. Let's just make that a bit bigger. You can see that okay at the back? One more step. There we are. So this is the configuration for a webhook. So what we can do is, up here, the resource kind is this webhook configuration. I'll keep that out of the way. I've got to give it a name. The key bit really is this API group. So what I'm saying here is, which API group am I operating on this webhook? So this case is v1, create operation on pods. This feature policy basically says what happens if the webhook technically fails. In this case, I'm saying it should fail. It should treat it as a failure. And then the final step is the actual webhook itself. And in this case, I'm using Azure Functions for the webhook. So it's outside of the cluster. And then depending on, you need to have certificates set up potentially if you're doing this internally. Luckily, this one works without that. That's not production-ready configuration, so please don't use it like that. So now I've written the webhook itself. Let me show you. I can show you that in the Azure Function portal, but I'll show you here. It's a bit easier to see. So this is a Azure Function, Node.js Azure Function. Hopefully people are reasonably familiar with it. There's not too much code in here. So we're basically going to get the request body, and we're going to essentially parse out the spec for the containers. And then in this example here, what I'm doing is I'm looking for an image name. So I'm saying that if that image is this particular one, I'm going to reject this. I'm going to say this isn't a valid. I'm not allowed to deploy this. So the key bit is really sending this admission response back. So in this case, I'm sending it back as a failure, and it's wrapped up in this admission review. And then the rest of this just standard HTTP. So we send that back. So let's see if I can get this demo to work. So I have this portal. I'm just going to refresh it so it hopefully loads. So this is that same code running in Azure Function on the portal. Sometimes the logs, I'm going to tempt fate now. The demos tended to have worked, but the logs don't always show. But we'll see if I've just tempted fate now. So let's run that. OK, so we see this error. That's nothing to worry about. It's basically some initial validation failing. So I'm going to clear that. I'm going to come over to the deployment. So I've got two deployments. I've got this v1, and you can see that's using the image, which is going to be rejected. Then I've got a v2, which is using v2 of the image, which should be successful. So if I come over to, I just need to set my context to I'm running this on the Docker for desktop. So there should be no deployments at the moment. Good, OK. So if I now apply v1, .yaml. If I now do get pods, we'll see no resources found, no pods found. If if I come over to my portal, where has it gone? There. So we can see, hopefully, let's see if I can zoom in. We can see, whoa, that's a little bit too far. Yeah, this is getting, hopefully you can see down here, it's run the validation, and it said it's bad image, and returned successfully. We can see, I'll just escape out of that. If I come over to here, if I do get events, we should also hopefully see that here. So we can see error creating admission webhook, denied the request, hello world is using a bad image. So that failed that request. Just to show you that it's not failing on everything, if I now deploy the V2, get pods, we should see the pods running on that. So, oops, there, so it's just that. So just a really quick demo just to give you an idea of how we can use the admission controllers. Let's go back to the slides and carry on. So we've seen these admission webhooks give us the ability to kind of take some control. What if we want even more control? What if we want to build abstractions on top of the Kubernetes resources? So much like Kubernetes as itself with deployments, which are an abstraction on top of replica sets and pods. What if we want to create entirely new resources within Kubernetes? We want to deploy our domain-specific components, for example. And we want to be able to use kubectl to manage them. This is where we have a number of options really on how we can extend Kubernetes. One is to write a custom extension API server. This is a lot of work. You have to write a whole API server. You have to write the persistence layer for the API server. Another option is to use custom resource definitions. This is probably the thing most people have heard about. Certainly the area of the hot topic area within Kubernetes. And we have these custom controllers. Now, often custom resource definitions and custom controllers are used interchangeably, and technically they're not. So talking specifically about custom resource definition, CRDs, this is essentially a new resource type that you can put alongside the existing resources. So just to clarify, for those who are not necessarily familiar with the term, the resources are things like pods, deployments, replica sets, config map secrets. What we can then do is, once we've created these custom resources, we can use kubectl to create and delete and interact with them, just like they were native resources. And these are stored within etcd, so we don't have to worry about our own custom storage for storing these resources. But they're pretty useless without a controller. So often people talk about CRDs. What they're really talking about is operators. I'll get onto that in a second. So let's have a look at how we create a custom resource definition. Again, this is actually not too tricky because it doesn't do a huge amount. So here I've got a custom resource definition resource kind. I have to give it an API group. So this will typically be your company name or whatever. We version it, and then we can scope it. So we can scope a resource to be cluster-wide or namespace scoped. And then we can define essentially how we interact with it. So it's a foo as a singular, it's foos as plural, and I've even got a short name, FO. Now what I can do is I can create a custom resource. I can create this foo object. So much like anything else, now I'm creating against the API version I've specified, creating a foo resource. And I can then write pretty much wherever I want down here in the spec. As I said, with this, it actually doesn't do a huge amount. So this quick kind of video will show we can create a custom resource as created. So what we can now do is deploy an instance of our custom resource. If I can type. And now what we can do is we can use kubectl, we can do get foo. That's pretty cool. I can do get fo because I've got the short name for it. And then I can do delete fo. That's about it. That's all I can do. There's nothing else happening here because all I've done is basically persisted this object to my database. So to add the logic, you need custom controllers. The interesting thing with custom controllers is they don't have to be only on custom resources. You can write a custom controller to operate on any of the existing resources. As I said, they're often paired with CRDs, custom resource definitions, because you want to add behavior. You don't just want to store that object to the database and retrieve it. You want to do a bit more than that. Typically, they're implemented in Go. I'm not sure if they have to be, but they use the Go client library to access the API at quite a low level. So you often see them written in Go. And you often see the term operator mentioned. And I guess informally, the term operator refers to the CRD plus the custom controller. Now, again, hopefully you're not having to write these yourself. There are actually a large number of them already out there. Most of the big companies who've got a need to do it have created them. So, for example, AWS has these operators which allow you to provision AWS resources as part of a Kubernetes deployment. Now, going into details on how we create an operator, or how we create a custom controller is beyond the scope of this talk, really. If you're interested, I would recommend going on a workshop. I've been on a workshop that's really useful. And there's also the CoreOS team released this operator framework, which allows you to kind of helps you. But it's still non-trivial tasks. So if you really want to extend Kubernetes, you've got to understand, there's got to be a good driver for it, not just because it's cool to do. OK, we're going to have a crunching gear change now. So we've talked about kind of positioning pods. I want to talk a little bit about scaling applications, and in particular, one area of this. So when we look at how we scale applications at the moment, we've got the horizontal pod autoscaler. It's probably the component most people are familiar with. It's arguably a fairly basic component to understand. And what that lets you do is it lets you scale your number of pods of your application based on metrics. The standard pod autoscaler does it based on memory and CPU. And then the V2 pod autoscaler allows you to do custom metrics. It's a lot more powerful, and that's pretty cool. But you can only scale your pods up to the capacity of your cluster. So if we want to scale beyond that, we have the cluster autoscaler. And the cluster autoscaler, just to differentiate that from the autoscaling that you may get from a cloud provider, which is typically based on CPU or queue lengths, the cluster autoscaler looks at pods that are waiting to be scheduled. So if there are pods that can't be scheduled because there's not enough resource, that will then trigger a scaling of the cluster itself. Now, how that scaling happens depends on your cloud provider. But obviously, scaling a cluster is not something that happens very quickly. It can take minutes. Maybe it takes 2 or 3 minutes. Maybe it takes 5, 6, 7 minutes. You imagine you've got to spin up a new VM, you've got to boot it up, you've got to bring it into the cluster, then make it available. What if your load is a lot spikier than that? So this is where this virtual kubelet project comes in. So virtual kubelet was a project that was created by the Deis team, which is now the Microsoft team, who work on the Kubernetes area. And essentially what it is it's a component that allows you to connect external compute resources into your cluster and make it look like a node. So you interact with this compute through the familiar Kubernetes API, but it's actually running outside of your cluster somewhere else. We take a look at how this works. Hopefully that's quite clear. So what we've got here is I've got my Kubernetes cluster. I've got 3 nodes within there. That could be bare metal, it could be virtual machines. And when I deploy this virtual kubelet, it creates a further node in my cluster, what's called a virtual node. And that node implements the APIs that Kubernetes is expecting for nodes and for dealing with pods, but the underlying compute is somewhere else. So Kubernetes sees it as another node. We can deploy resources to it, we can deploy pods to it, but they're running somewhere else. There are a number of implementations of this virtual kubelet. No surprise, really. The first one they did was the Azure Container Instances. So Azure Container Instances, for those who aren't familiar, is kind of Microsoft's, Azure's serverless container platform. So it allows you to spin up containers onto ACI without having to provision any VMs or anything else beforehand. You pay per second for the containers are running. As soon as you shut them down, you stop paying for them. AWS Fargate is very similar, AWS equivalent. And then the implementations of this for Nomad, Service Fabric Mesh, IoT, and then many others as well. The virtual kubelet project has been donated to the CNCF. It's now an incubator project as part of the CNCF. So where this becomes quite interesting is when we want to handle some spike in our load, and we want to potentially use this instead of relying on a cluster autoscaler. So imagine I've got this cluster, and I'm kind of managing with my load, and then suddenly I get a spike in traffic. What I can do is use the virtual kubelet, which is actually, it's probably worth clarifying. The virtual kubelet is a project, and then implementation of that is a virtual node. So often those two terms are probably a little bit confusing. So what we can do is, by having the virtual node there powered by the virtual kubelet, we can spin additional containers onto ACI to handle that spike in load. And while our clusters potentially auto-scaling in the background, we're able to handle the traffic. Once our cluster's up to scale, we can start shedding the load off the ACI. We stop paying for that at that point, and we are happy again. The virtual node is an AKS, is built into AKS now. It's in public preview, so it was in private preview up till recently. If you're creating a new cluster, it's just one option now down here. Just enable this option. So let's have a look at that virtual node and scaling. So let's come over here. So I'm just going to switch clusters. Oops, I can't type because everyone's watching. So, okay, get notes. So, what we can see there, just try and make that, is that okay? So what we can see is I've got 3 nodes, standard nodes in my cluster, and then I've got this 4th virtual node. This is the virtual node that was added by ticking that option. So this is a virtual kubelet-powered node. If I have a look at that node, actually, let's grab. So let's have a look at describe. So we can see it looks like any other node. We've got these labels on there. One of the labels says it's a virtual kubelet. And then the bit that's probably important to mention is it's tainted. So kind of coming back to the concepts we talked about earlier, we've got a taint on it. So what we're saying is that unless you tolerate this taint, you're not going to be scheduled on this. And that's what we want. This is a virtual node. We've got physical nodes in our cluster already, physical or virtual machines. Why? We don't necessarily want pods to be deployed on there for no reason. We want those only if there's a need. So let's say we have a need. So what we can do is I've got a deployment running. Actually, just clear this. So I've got this online shop deployed. There's a few other things which you just ignore for now. We've got this online shop here. And it's running at the moment. And if I do get pods wide, we should see, sorry, it's wrapped around a little bit, so it's maybe not so easy to read, but it's running on the AKS node. It's running on the agent node. Now, if I look at the YAML for this, so let's flip over and have a look at that. This is the YAML for that. And what you can see is I've got 2 components that we've talked about before. So I've got a node anti-affinity here. So what I'm saying is, match, keep out of the way. So here we are, we're saying match it when it's not in the virtual kubelet. So this is basically saying don't schedule it on the virtual kubelet, but it's a preferred. So we're saying prefer not to schedule on the virtual kubelet, but at the same time we are tolerating the taint that's on the virtual kubelet. So what this will do is it will say, by default, I'm not going to deploy to the virtual kubelet, but I can if I need to. That can if I need to, maybe when you've got a sudden spike in traffic. So let's see if we can show that. So if I've got to juggle a few windows now, so let's see if I can get this right. And not that one. Just going to have to reconnect the Cloud Shell. So I've got App Insights connected to this application. I'll show you that in a second. And what I'm going to do in the Cloud Shell, I'm going to spin some loads. So I just need to grab the load test. And just before I spin that, what I'll do is I'll show you the front end. So the front end is it's basically a Contoso kind of electronics store, pretty basic stuff. And you know, let's say Black Friday is happening. Black Friday is probably a bad example because you can predict the load in Black Friday. But let's say we've got some flash sale on, and we're going to get a sudden spike in traffic. So what we'll do is, if we come back, I need to juggle a few windows. So let me clear this. And I'm going to do kget pods wide again. Oops, kget pods. And we will now kick off the load. So I'll come over here and I'm going to start this load test. If we watch these metrics here, what we see at the moment, we're getting literally like one request. See, suddenly now jumped to 200 requests per second. The request duration suddenly jumped as well initially. So we're seeing this jump up from pretty much 0 to 500 milliseconds. What's happening now is that load is being detected by the pod autoscaler. That's starting to provision new pods of this application. And because we've got that taint and we've got the virtual node, it's actually spawning instances onto that virtual node. So that's how quickly it's happening. You see that response time is starting to drop. So if I now come back to console, if I now do get pods again, what we should see is a lot more pods. You see these online store, and they're running on the virtual node. Oops. So these are all now running on the virtual node. If I keep that running, that'll start spinning up more. You can see it's even more now. So if I do kget HPA, just try and move that up. We can see we've got a maximum of 60 pods and it's spinning up. So the response is quite quick, as hopefully you can see. That app is still there, by the way. It's not smoke and mirrors. And if I come over to Azure Container Instances, if I refresh this, what we should see is, where are they? Strange. We should see a load of pods, a load of container instances. Maybe they just haven't quite shown up yet. It's lagging, but they're clearly being created. As we can see there, so there's some already running, some are waiting, some are being created. So the key thing is the response time for this. This wasn't taking minutes for a cluster to scale up and become available. We've actually started responding within a few seconds. Now, if I kill that load, then we'll start shedding the pods off that load. And within, I'm not going to wait for it, but within about 2 or 3 minutes, we'll see the number of container instances dropping. And eventually, we'll go back to steady state, which is just running on our provision nodes. So hopefully, you get a good idea of how we can use something like this to have very flexible load. The other interesting prospect this opens up is maybe not having any actual VMs in my cluster, not paying for any compute that's sitting there not being utilized. Certainly something that I think I wouldn't be surprised to see in the future. At the moment, it's not possible. You can spin down to a single node cluster and do this. And I suppose technically you could switch off that node. It's not a supported scenario, but you could certainly switch off that node and you probably force everything to go onto the ACI, but it's definitely not a supported scenario. Don't tell anyone I suggested that. Probably have to delete that from the recording as well. So hopefully that gives you an idea of that concept. Now let's go back to the slides. I think I'm doing quite good for time actually, which means we can go and get coffee quickly as well. So the final section was the bit I said I didn't want to spend too long on. It's around service meshes. So how many people here have interest in using service meshes? So anything like Istio or looking at Istio? There's a few people looking at it. Cool. It won't be anything too new for you. So what's a service mesh? Again, apologies if you were in Elton's talk, probably repeating. So service mesh is infrastructure layer for handling service-to-service communications. So its job is basically to allow you to deliver reliable, delivery of requests across complex, cloud-native applications. Why do we need it, though? Well, what Kubernetes is built in for networking and service-to-service communications is pretty basic. I'm sure you'll agree. We have pod security policies, and then we have ingress. And even the ingress is pretty lightweight. Allows us to do some basic routing on host name and host headers. Other than that, we can't do anything. We can't do any canary deployments or anything like that. When we have the ability to control the traffic, we can actually open up quite a few powerful kind of application scenarios. So I mentioned canary deployments, allowing us to deploy second version of our application and sending a limited number of users to that instance. Another option that I quite like, which I don't see talked about as much, is launching darkly. So this is where you launch a second version of your application, and it sits there and receives a mirror image of the traffic that's going to your production instance, and you can see how it behaves with real traffic. So we can test everything we want in test environments. Reality is, until we get into production, that's when we hit it with real traffic and we find out how our application behaves. So by mirroring the traffic, what we can do is send essentially a copy of the same traffic to another instance of the service, where we can watch it. If we're doing some kind of refactoring, we can actually inspect the inputs and outputs and make sure that they are matching. And then we can, when we're happy that it's behaving the way we want, we can then do a swap over. And then also, what service meshes let us do is do traffic routing between legacy applications and cloud-native apps. So with something like Istio, and I'll talk a bit more about Istio in a second, you can actually expand a service mesh into VMs. So you can have VMs and then have Kubernetes cluster running service mesh. So Istio is the most well-known service mesh. It's an open source project being led by Google, Lyft, and IBM. And it runs on top of Kubernetes, but actually does support other platforms as well. So it provides a number of features. So network error handling. So it allows us to have retry logic, circuit breakers, timeouts. Now, these are things you can build into your code. Of course, you can. But the challenge is, if you're running different languages in your cluster, if you're a team that operates different languages, you've got to implement the same logic in multiple languages. By pushing this kind of concern into the platform, you have a consistent approach in dealing with it, and your applications don't need to have these additional libraries just to handle this logic. Similarly, we can do rate limiting. So if you've got a bad actor in your cluster, you can throttle the rate it sends requests. You can do this traffic shifting and monitoring. So I talked about before this canary deployment, sending a percentage of the traffic. Istio lets you do quite powerful concepts by sending only certain users seeing different traffic. And then this mirroring concept, as I said, it's not used that much, but sending an exact copy of the traffic to another instance as well, rather than sending some percentage. Istio lets you do fault injection. So this is quite powerful if you're testing your microservices deployment. So a key aspect of microservices is that they shouldn't be reliant on all the other services being up at the same time. So you can test that by injecting faults. And you can also secure the service-to-service communication. So again, one of the challenges in a big cluster is you want to make sure that traffic between services is controlled, it's encrypted, and you have policies that prevent certain services from talking to other services. And then finally, I think there's one more. You can see the requests. So in modern kind of microservices applications, we have multiple components made up, handling the request. So with the service mesh, you can see that request as it flows through your application. So just to wrap up, and I think pretty good on time, I've just touched on literally the handful of things that Kubernetes lets you do around pod scheduling. And there are many, many other concepts in Kubernetes that we could spend probably a week talking about. I've hopefully shown you how we can use admission webhooks to customize our creation of our resources without too much code. And if you really want the ultimate flexibility, then you go down the custom resource and controller route. And the virtual nodes, as I said, I think it's quite an interesting concept, and it's not a Microsoft project anymore, so I'm expecting to see a lot more uptake on this. especially now it's a CNCF project. But yeah, potentially having these serverless Kubernetes clusters in the future where we're not even having to worry about the VMs anymore, the nodes. We're just running, essentially managed Kubernetes providers at the moment have given us, they've taken away the API server. We're not managing that anymore. So as soon as we use a serverless platform underneath, then we've got rid of everything. And also those people like arguing whether serverless and Kubernetes is one way or the other, we can just stop the argument. So if you want to learn more, obviously a lot of what I talked about is in the Kubernetes documentation. It's not necessarily the easiest thing to get hold of. That demo I showed you is on GitHub, the virtual node autoscaling. It's a little bit finicky to get set up. Feel free to ping me if you're trying and having problems. I mentioned I wasn't going to deep dive on microservices. I did a talk at NDC Sydney last year where I did spend a bit more time and I did a few more demos. Of course, again, Elton did a talk here, so you can catch his video as well. And finally, Katacoda is awesome. I always plug Katacoda. I don't work for them. I always plug Katacoda because I think it's a fantastic platform. Anyone here not heard of Katacoda? Speaking to the converted. They've got a course on there for the operator frameworks. If you did want to learn more, you can have a look at that as well. And then I think on that, we've got some time for questions. Hello. Remind me to repeat the question if I don't.
Custom resources.
Yeah.
Is that what's used if you want to create the cloud-native database instance, for example?
Yeah, so a lot of the database companies have created operators, and so has AWS. So I think AWS has got a set of operators now, including creating AWS databases using a custom resource. So you would create a database instance in there, and it gets deployed. There's another project which I didn't have time to cover. It's around the service catalog, which is a different approach to doing a similar concept of provisioning external resources as part of a Kubernetes deployment. But that goes down a slightly different route. It's using an API aggregation approach. But the end effect is similar. But I think they're looking at converting it to a custom resource approach as well, because it feels like the more intuitive way. Like there's a Prometheus operator. I was actually using that in my demo, you may have noticed. It just simplifies the deployments, but yeah. Anyone else? Elton?
So when you talk about pod affinity, your example was having my web pod on the same node as my cache. But if the cache is in a service that's going to go through a load balancers, it's not necessarily going to hit that pod on the same server. Or does the affinity interrupt the load balancer too?
No, that's a fair point. No, it doesn't affect it's more around what's currently running. So yeah, the load balancer will do its thing. It doesn't affect the load balancer as far as I understand. But yeah, it's a good point though. I didn't think of that. Somebody else?
You talked about the virtual node.
Yeah.
Does it scale your actual cluster node as well? Does it add that, or is that a manual operation that you need to do? For example, I have 3 nodes, and then I get a lot of load, and then this virtual node starts kicking in. How does my cluster get a new node? Is that something manual?
So I'll repeat the question because I forgot to do that for the first 2. So the question is, does the virtual node automatically trigger a cluster autoscaling at the same time? The answer is no. It's purely around the virtual node. But there's certainly something you could have the cluster autoscaler probably wouldn't work in that situation actually because the pods won't be waiting to be scheduled. So yeah, I think you'd have to probably trigger off the horizontal pod autoscaler and use that as some kind of initiator. But yeah, no, it's certainly not built in. It's a nice idea, though. It depends. I guess the problem is if the load is very spiky, then you probably want to keep it on the serverless containers because you don't want to have the extra capacity provision in your cluster the whole time. So it's a bit of a balancing act on that.
I heard that Microsoft was going to give this functionality in AKS that you could have your nodes autoscale as well, cluster node, but now I see that there is other virtual node thing instead of that.
So the cluster autoscaler is in AKS. It's in preview, but it's there. So you can set that up. But if you use that in conjunction with the virtual node, then the cluster autoscaler won't kick in because it won't find, at least I don't believe it will kick in because it relies on pods waiting to be scheduled. But if those pods are, so if you didn't tolerate the taint on the virtual node, then certainly the cluster autoscaler would kick in because then there'll be pods waiting to be scheduled, which aren't going onto the virtual node. Cool. Any more questions? In that case, I'll say thank you very much, and probably got 5 minutes for coffee.